Hi everybody, we are on chapter 12, section 1, testing goodness of fit. So you might have noticed that we skipped chapter 4. We will be going back to chapter 4 after going through this to take a look at scatter plots and lines of best fit. So it just fits in better with what we're doing now. So find the critical values of the chi-square distribution and perform goodness of fit tests. So let's start. Now, the hypothesis tests for qualitative data, also called categorical data, are based on a chi-square distribution. The test statistics for these tests is called chi-square statistic, and as we went over before, this is the Greek symbol here for chi, so this is chi-squared. So there are actually many different chi-square distribution based on the degrees of freedom, and we also looked at this before. So here's a degree of freedom of 1, here is a 5, here's 10, here's 20, here's 30. Now, chi-square distributions are skewed to the right, and the values of the chi-square statistics are always greater than or equal to 0. They are never negative. So let's find alpha is at 0.05 critical value for the chi-square distribution with 12 degrees of freedom. So if we have a critical value is 21.026, it's found that the intersection of the row corresponding to 12 degrees of freedom in the column corresponding to alpha at 0.5. So here's our 12 degrees of freedom, here's our 0.05, and the intersection of it will give us the critical value of 21.06. Now, performing the goodness of fit test, imagine that a gambler wants to test a die to determine whether it's fair or not. The roll of a die has 6 possible outcomes, and they are all equally likely if the die is fair. So the gambler rolls the die 60 times and counts the number of times each number comes up. The results are presented below. These counts are called observed frequencies. So the gambler wants to know, is your die fair or not? Do you have it weighted? So he actually does 60 rolls, and this is what he gets. Now, the expected value is going to be, let me go back. The expected value for each one of these would be 10. 10 here, 10 here, 10 here, 10 here, 10 here, and 10 here. Because if the die is fair, then each value has a 1/6 probability of getting chosen. So 1/6 times the 60 times that he rolls, we should get 10, 10, 10, 10, 10, 10. Now, are the observed outcomes different enough to conclude that something's wrong with the die? So the null hypothesis for this test says that the die is fair. So we're saying that it has a probability of 1/6 of occurring. We're going to let p sub 1 be the probability of rolling a 1, p sub 2 of rolling a 2, etc. All of these are equally likely. So 1, 2, 3, 4, 5, 6. They're all equally likely. They are all 1/6. The alternate hypothesis says that the roll of the die does not follow the distribution specified by the null hypothesis. So in other words, it states that not all of the p sub i's are equal to 1/6. So we're saying something's wrong with the die. Maybe. We're going to test it. So to test the gambler's null hypothesis, first we begin by computing the expected frequencies, and that's what I went over already with you. The expected frequency would be the probability times the number of trials. So this would be 60 times 1/6, 60 times 1/6, etc. And that's how we get the 10. So when we compute the expected frequency for the gambler rolling a die 60 times, we're going to get all of them equal to 10. So if a die is tossed 60 times and the outcomes on the die are equally likely, we expect the outcome to occur 10 times. The table shows the outcomes and the observed frequencies and the expected frequencies. So now here's our table. These are our observed frequencies. These are our expected frequencies. Now, if the null hypothesis is true, the observed and the expected frequencies should be fairly close. The larger the differences are between the observed and expected frequency, the stronger the evidence is against the null hypothesis. So the statistic that measures how large the differences are between the observed and the expected frequency is the chi-square statistic. So let's let K be the number of categories. So here's our number of categories to be the observed frequencies, and the E subnumbers to be the expected frequencies. So the chi-square statistic would be the observed minus the expected quantity squared over E, and we're going to do the sum of all of those. When the null hypothesis is true, the chi-square statistic is going to be approximately the chi-square distribution, but only if all the expected frequencies are 5 or more. So first you have to check and see if your expected frequencies are 5 or more. If they are 5 or more, then you can continue to use this chi-square statistic. So we're going to state the null and alternative hypotheses. We're going to compute the expected frequencies and check if they're 5 or more. We're going to choose a significance level that we want to measure the difference on. Then we'll compute the test statistic. We'll find the critical value from table A4 using K minus 1 degrees of freedom, where K is the number of categories. So if chi-squared is greater than or equal to the critical value, we're going to reject the null hypothesis. Otherwise, we do not, and then we'll state the conclusion. So let's go through and do that. So here's our observed frequencies. The null hypothesis we know is that it'll be equal to 1/6, the probability. The alternate hypothesis says some or all of them will differ from 1/6. So now we're going to compute the expected frequencies, which we already did that. We know they're all 10. So we're going to compute the chi-square statistic. Here shows our table. Here's our observed, expected. Here's the difference between the two. Here's when we square it, and here's when we divide it by our expected. So when we do that for each one, these are the values that we get. So these are our chi-square statistic right here. So there are 6 categories, so the degrees of freedom again was 5. So we have from the table, we'll take a look at 0.5 for the critical value of 5, and the degrees of freedom are 11.070. We don't need that other 0. The value of the test statistic then is 9.4. Now you say, well, where did you get that? Well, this is the sum of all of these. So you have to add these together. So once you add these together, you get 9.4. So now, since 9.4 is smaller than the number that we got from the table, we do not reject the null hypothesis. So there's not enough evidence to conclude that that die is not fair. So here we have the technology to use the goodness of fit. We have our expected and our observed. We can do it in Excel, which I love Excel. And here's the chi-squared statistic here, getting your value. We can use our TI-84 plus, putting in our lists, going to chi-squared. Here's our test, using our list 1 and list 2. Degrees of freedom, and there's our value. So either way. So what we should know from this is how to find critical values of chi-square distribution, how to perform a goodness of fit test, and that is it for 12.1, and I'll see you soon for 12.2.